too hard on my computer to do that, so I'll just put the arrows like this. How many local extremes do you have? 3. Local min, local max, local min, right? Global extremes.
3.
Global. What's your global minimum?
The bottom.
Bottom. Global max.
Goes to infinity.
These go forever. So we will say there is no global max. That's what we'll say. Because if you said that there was a global max, you would need to give it a value. And we never assign it a value of infinity. So we just say there's no maximum. If you try and tell me that there's a highest point on this curve, I would argue with you I could find one higher. Yes?
What if there's 2 maximums that have
the same y value? Then the value is, whatever y value it is the maximum. I think what you're saying is this. Let's say we have let's just take a parabola like this, right? Then we would have one local extreme, right? This would be our local extreme. We would have a global minimum, and we would have, both of these would be global maximums. But it would be the y value is the maximum, because they would share the same y value, wouldn't they? Hey. Hey. I think this is what you meant. Right? How many local extremes? 3. Does that mean every function has 3? No, just the way I'm putting them up here, okay? You could have, think of the sine curve. How many local extremes does a sine curve have? Well, you depend on where you cut it, right? Okay, I have local min, local max, local min. Yeah? Local min, local max, local min. Global minimum. Global. There's two of them, right? It happens at 2 places, right? It happens at 2 places, but it's the same minimum value. The minimum value would be the y coordinate. Then we have 2 global maximums, don't we? 2 places where it occurs. So I'm going to label these. These are your globals, right? Global, 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 global. And then our locals. Again, this is very geometric, right? Very visual. There's, y'all following it? Okay. And now we get to a very important theorem. It is called the extreme value theorem. If f is a continuous function, that means I can draw it without picking up my pencil. So you've got this function you can draw without picking up your pencil, and it's defined on a closed interval. That means I start somewhere, I end somewhere. And if you want, this would be a, and this would be b. Understand? A function f defined on a closed interval where that is a continuous function that I can draw without picking up my pencil. If we ever have that, then what? Then what? You have to have it, you must, there's no way to avoid it. You must have a global maximum and you must have a global minimum. It has to happen. As long as you can draw without picking up your pencil, and as long as it starts and ends at 2 points, it's defined at those 2 endpoints. That's another key. It has to be defined. That's why it's important to say closed interval. You understand the difference between closed and open?
What if it was a linear function with a slope of 0?
Good question. Let's talk about that after we get through a few of the visuals. All right. You must attain both an absolute maximum and an absolute minimum. here's a visual of what we're talking about. All right, so what's that? You see a typo?
Under values of cube 1.
Values of Q, oh, okay, yeah. Where, I can fix it pretty easily. Just got to find it in my code. It's right. Wait, oh, there it is. Curve. Thank you. I'm glad that you're paying attention to something up there. That's good. Well, that's pretty hard to notice. That's pretty hard to notice. So I'm. All right, there we go. So if I draw this curve, starts at this point, ends at that point, am I guaranteed that it attains both a maximum and minimum? Absolute max, absolute min. Yeah, it's continuous on a closed interval. The absolute max, absolute, looks like it's up here, right? Boy, that's really hard to tell if that arcs back down. Does it look like it arcs back down?
It does.
It does. So the absolute max is probably somewhere around here. Oh, you know what? I already did this. There it is. Okay, there's the absolute max. The absolute min is right there. Got it? That's one example. Here's another example. Same two endpoints, right? Do I have an absolute max and min? Yes, absolute max right there, absolute min right here. It's impossible to connect these two dots with a continuous curve and not get a highest and lowest. It's impossible. Straight line. Absolute max and min are the two endpoints. How about that one? It's not continuous. It's not continuous. I don't have to have an absolute max and absolute min, right? Extreme value theorem does not apply. So if you have a break in the graph, the deal is off, okay? The deal is off. But if you can draw without picking up your pencil, then I guarantee it's going to happen. Now that leads us to Fermat's theorem, not Fermat's last theorem, if you're familiar with that. Fermat's theorem says if f has a local maximum or local minimum, local, not global. If f has a local maximum or minimum at the point C, and the derivative exists, then it must be 0. Okay. If a function f has a local maximum or local minimum at a point C, and the derivative exists, the derivative must be 0 there. Let me try and draw this for you. So look at this function right here. Do you agree that there is a point C, right? Or it's actually the x value on the x-axis, it's C. Do you agree that there's some point C where we have a local maximum? Is that a local maximum there? All right. Does the derivative exist there? Look at it. Look at the picture. It's nice and smooth, right? Does it look like the derivative exists? And what is the derivative? 0, flat tangent line, right? The theorem says if you have a local maximum or a local minimum and the derivative exists, then the slope of the tangent line there has got to be 0. All right, opportunity for bonus, but you got to be on camera. You ready? Anyone who can come up here and draw me a function that has a local maximum where the derivative does not exist. Oh. You can do it? Okay. 5 points on your next exam. But I'll take away 5 if you get it wrong. No, I'm kidding. I'm kidding. No, you can do it right here. You can do it right here.
So we're like, see like that.
Okay, so any function where it has to have a local maximum, but it would violate this. In other words, the derivative wouldn't exist. Five points. You're done. Good. Good job. Remind me. Does this have a local maximum?
Yes.
Yes. Does the derivative exist there?
No.
No, because it's a corner, right? Derivatives don't exist at corners. Fermat's theorem does not apply to this. Fermat's theorem says if you have a local maximum and the derivative exists, then it has to be 0. If the derivative doesn't exist, he's not saying anything. Do you understand? The theorem does not apply to this situation. Very good. So there's an example. Here's an example that fails. Look at that. It's like you knew. It's like you knew. See that? Local maximum, derivative doesn't exist, theorem's out the window. Can't use it. Another example that fails. This would have been, you could have also done this. Although I said show a local maximum, right? This doesn't have a local maximum, right? So look at what this is showing us. Is the derivative 0 there? Does the derivative exist?
Yeah.
Is it 0? It's right there. Flat tangent line? Yes? So you have the derivative exists and the derivative is 0. Does that mean you have a local maximum or minimum? No. So we have to be very careful about things here. Just because you have a derivative equal to 0 does not mean that you are at a max or a min. Right? There's an example. Derivative is 0 there. You're not at a local max or a local min. The theorem is out the window here. Theorem is out the window because the theorem says very specifically, if, what's the first condition? If f has a local max or min. That picture I just showed you didn't have one. So you can't use it. How are we doing on time? All right, we're doing okay. All right, so as good as that theorem is, we need another way, because the theorem, it's helpful because it gets us thinking, but we're going to have a different way to attack these problems. But before we can attack them, we need to define something. What's called a critical number of a function. So if somebody hands you a function, okay? Doesn't matter what it is. I hand you a function, and I ask you to find me the critical numbers. The critical numbers of a function are any numbers where the derivative is 0 or where the derivative doesn't exist. Because basically what we can say is this. We know that anywhere the derivative is 0, we have a flat tangent line, right? Anywhere the derivative doesn't exist, something else weird is happening. And these are places we're going to want to look in order to determine what our function's doing. These are going to be, these numbers that we find here by solving these equations are critical for us to determine maximums and minimums. Therefore, we call them critical numbers. We have another extension of Fermat's theorem. This one is pretty important. I'll highlight it. If f has a local maximum or minimum, right? If you have a local max or min, even the one you just drew with the v, right? Or the whatever, the point. Guaranteed that at the where you're having the local max or min, where that happens, at that point C, guaranteed that c is a critical number. Which means that at the place that you're looking, the derivative is either what? 0 or does not exist. It would be impossible for anybody to draw me a function with an that has a local maximum or a local minimum where the derivative is either not 0 or does not exist. You would have to have one or the other. Like the one you drew for me, your derivative didn't exist there, right? That would be a critical number.
What about that one function that has like functions inside it? It's just like a sawtooth, and just when you zoom in, it's got more sawteeth.
That was an example of a continuous function that is nowhere differentiable. That means that the derivative wouldn't exist everywhere, but you're actually going to have an infinite number of local maximums and mins. On every one of those saw teeth, at the top of every tooth is a local maximum. At the bottom is a local minimum, but there's infinitely many because your derivative doesn't exist at every single one of those points. I never answered your question. What would happen? What about this? Sorry, I never got to this. What if you had that function, flat line? Does it have an absolute max?
Yeah.
And let's just define this. You know, I'll put a x and y axes in here. Let's just say that this is 2. So that is really like y equals 2, isn't it? And let's say it's defined between 1 and 5, just to give it a closed interval. Then what's the absolute maximum? 2. What's the absolute minimum? 2. The absolute max and min are the same number. That's how you would answer that. Yes?
Could you define a local when the tangent line, the slope is going from negative to positive or positive to negative?
What about it?
Could you define, like, you were talking about neighborhood or local? Could you define it when the tangent line, the slope is going from negative to positive or positive to negative?
The local, yes. Yes. Yes, you could. And you're thinking actually ahead. That's what we're going to do in 4.3. Okay, in 4.1, we're going to focus all of our attention on closed intervals. Once we take that closed interval condition off, it gets harder. And that's how we'll go after it. All right. Now here's the big daddy right here. All right, if there's one thing you're going to take away from today, this is it. 4.1.11. How to find the absolute maximum, minimum values of a function on a closed interval. The method that's laid out here is the method that you can use in any class. Any class. If someone gives you a function, and that function is continuous, and it is given to you on a closed interval, you can always find the highest and lowest points. Always. And this is the method to do it. What we will do is we will first make sure it's a continuous function on a closed interval. Then we will find the critical numbers of the function. What are the critical numbers? Wherever the derivative is 0 or does not exist. We will have to figure out where that happens. Once we actually find those, we're going to plug those answers, we're going to plug those numbers into the original function. And then we're also going to plug the endpoints into the original function. Here's a way of me explaining this in visually. Let me try and visualize this method. Let's say that I have a function that's defined on 1, 5. Okay? I'm going to give you some more information here. What if I tell you that the derivative at 2 is 0, and I tell you that the derivative at 3 does not exist? And I also tell you that this function f is continuous, all right? How would you determine the highest and lowest values? Well,
We know that 2, it's 0, so it's got to be some.
you have a flat tangent line, right? So at 2, I actually don't know how high up or down I am, do I? But I know that the slope of the tangent line there is 0, right? The slope of the tangent line there is 0. So I'm just going to make this up. It could be here, right? It could be here. It could be up there. I don't know. But the slope of the tangent line is flat. At 3, the slope of the tangent line is what? Doesn't exist, which means it can be a corner, a cusp, but it can't be a discontinuity. Why? Because I said it's a continuous function, right? So it's either a corner or a cusp. Or it could also be a vertical tangent. If you remember, there was that other possibility of vertical tangents. Your tangent line runs vertical. That has an undefined slope. And that would mean that the derivative doesn't exist. So at 3, again, I don't know how high or low this point is, right? So you tell me, where do you want it?
Stop.
Okay, right there. Right there. I'm just making it up. That could be a corner, it could be a cusp, it could be a vertical tangent. The theorem says, that theorem says if you have a max or min, right? If you have a local max or min, then the derivative is either going to be 0 or does not exist there. So these could be local max or mins. These could be. And then the only other thing I need to consider is what's happening at the endpoints, right? Like the endpoints, I could plug one in, and it could be up here, it could be down here, right? I don't know again. And then this 5 over here could be, I don't know, it could be there. This is a totally hypothetical situation based on this information. What I want you to understand is that in order to find the absolute max and mins of a function on a closed interval, all we're going to need to do is figure out where this happens, at 2 and at 3. Then we're going to look at the endpoints, 1 and 5. And guess what we do with each of these points? We plug those numbers into the original function. The biggest number you get out is your max. The smallest number you get out is your min. So think about it this way. If I plugged in 1 here, let's say I plugged in 1 and I got 10 here. And then let's say I plugged in 2 and I got, I don't know, 4. I plugged in 3, I got -1, and I plugged in 5 and I got, let's say, 6 to come out. Understand those are the y values? Then what would my absolute max be? 10. What would the absolute min be? -1. But I could have drawn it different ways, right? So I could have drawn this point down here, and then this one could have been here, and this one could have been way up here, and then this one could have been down here, this one could have been here. And then I'd have different answers, wouldn't I? But it all comes down to just simply first identifying where these things are happening, and then plugging those numbers and the endpoints into the original function.
Oh, that wouldn't be your endpoint.
What wouldn't? Oh no, that wouldn't be my endpoint. I don't know why I put that there, sorry. All right, let's do an example. Once you see an example, you're going to be, I think, happy. We'll see. And we'll do a function that we could not do in college algebra. How about that? Something nasty. How about this? F of x equals x cubed, 2x cubed. No, sorry, x cubed minus 6x squared plus 5 on the interval -3, 5. What are the instructions here? Find the absolute maximum and absolute minimum of that function on that interval. So if you just graph this function between -3 and 5, you would have some picture, right? Tell me the highest value you ever get out and the lowest value you'll ever get out. So we're going to use the closed interval method. Why? Why am I going to use the closed interval method?
That's what we're studying.
Yes, because you realize this is a closed interval, and you realize that's a continuous function. And you're being asked to find the absolute max and min. So to do that, we apply the method. First step is to do what? What's that?
Plug it
Nope, not yet.
The critical number.
Find the critical numbers. Find critical numbers, which I will abbreviate CN from now on. Okay, critical numbers. Find the critical numbers. How do we do that? You need to figure out where the derivative is 0, right? That's the way I'm going to write it. I want to know when that happens, and I also want to know when the derivative does not exist. Those are the two things I have to do in order to figure out the critical numbers. I could put in here, find where the derivative is 0 and find where the derivative doesn't exist. Do y'all understand that, that these two statements are basically asking us to go figure out where the tangent line is flat and possibly where the tangent line is a corner, a cusp, or a vertical tangent? That's what those two things are saying? All right, so in both of those, in either one of these, I need the derivative, don't I? So let's take the derivative. Let's just get that first. What's our derivative? 3x squared minus 12x, and that's it. All right, so there's my derivative. I'm just going to look at it. There it is. I'm happy about that. There we go. Very, very happy. Now let me go and answer these two. First of all, where's the derivative 0? All right, well, take the derivative and set it equal to 0. So do you remember me telling you in the past, like, you always ask me, like, how far should I simplify the derivative? And I kept on saying, like, eventually we're going to set it equal to 0. Okay, that's what, now we're there, okay? So this is a pretty easy derivative. It's your first example. But they'll get a little more complicated, and this solution to this equation is going to require a little more work. But this is pretty straightforward, isn't it? Solve that quadratic equation. I can just factor it. Factor 3x out, like that, right? And then set each one of those to 0. So set that to 0, you get x is 0. And then you set this to 0, you get x is 4. These are two critical numbers. We have something interesting happening at 0 and at 4. Understand? Now I also need to ask myself where the derivative doesn't exist. So I'm going to do that right here. F prime does not exist. So it's not like this one. For this one, we just set the derivative equal to 0, right? That was an equation for us to solve. Asking where the derivative doesn't exist means that you have to go look at the derivative and figure out if there are any values of x that'll screw that thing up. Like, are you ever going to get division by 0? Are you ever going to get roots of negative numbers? Are you ever going to get any weird stuff that we can't handle happen? It's a polynomial, right? This is polynomial. The domain of that is everything. You can hand me any x and I can throw it in there. I'm never going to have a problem, right? So it'll always be defined. So the derivative never existing is not applicable to this. I mean, it's a polynomial. If you want to try and explain why, it's a polynomial function. The derivative is polynomial. It's well defined everywhere. That NA is not applicable, or you can just say doesn't apply, or so that's it. How many critical numbers do we have? We have 2 critical numbers, all right? We have 2 critical numbers. Before we proceed, you must do it one last check. Do these critical numbers live in this interval?
Yes.
Yes. 0 lives in there, and 4 lives in there. What if this would have turned out to be 7? Let's just say that was 7. What would it? We just throw it out. We wouldn't even look at it. Okay? We just chunk it. But these both live there. All right. We're ready. Last step. All I need to do now is evaluate the original function at the endpoints and at those two critical numbers. So I'm going to evaluate f at -3, 5, 0, and 4. Do you understand what I'm doing? I'm taking these 2 points and the 2 endpoints, and I'm going to plug all 4 of them into the function separately. So I'm going to have to do f of -3, f of 5, f of 0, f of 4. It doesn't matter what order you do these in, okay? It really does not matter what order you do them in. All right, plug them in. Yes, you have to actually like plug those in. -3 cubed is -27 minus -3 squared is 9. 9 times 6, 54, so minus 54 plus 5. What is that? Negative 76? Negative 76. All right. F of 5. 125, that's 5 cubed. Minus, let's see, 5 squared is 25 times 6 minus 150. And then plus 5, is that right? Yeah. Negative 20?
Yeah.
Okay, this one I've got. No problem. 5. And then last but not least, what do you get? 64
-27.
minus 6 times blah, blah, blah. Okay, minus 27. Anyone else get the same thing?
I just plugged the equation.
You got it in there and you're just pulling off points? That's fine. All right, negative 27. All right, what is the global maximum? What is the global maximum? 5. What is the global minimum? Negative 76. Pardon? Okay, we're not going to look at local max and mins until we get to 4.3. The closed interval method, which is what we just did, is used to find the highest and lowest points of a graph on a closed interval. That's what it's for. If you want to do locals, you got to wait till 4.3. All right? Now what I'd like to do, you'll have this information, yes? When I write down my global minimums and global maximums, I like to write them as points. -3, negative 76, and 0, 5. This was the max, this was the min, right? I like to write them as points because when I write them as points, I can not only tell you what the actual values were, but I can tell you where they happened. Now, we obviously don't have enough time to do another one, but this is perfect because I'm going to be able to graph this for you. Yeah, so I'm going to graph this function. X cubed minus 6x squared plus 5. But I'm only graphing it between, what was it, -3 to 5? -3 to 5. Well, that didn't work out very good. What was our min? Where was our min at -3? Is that right? I can't see it.
She put on Wolfram.
There we go. Okay. Yeah, that's no good.
Put on Wolfram and it's good.
Does it? I'm just messing with this, sorry. Negative. Good enough. There you go. Okay. It's hard to see it here, but our two endpoints, right, were -3. So there's -3. I wish it would have put the -3 up here, but it didn't. -3, and then the +5, right? And then the two critical numbers were 0 and 4, right? And look at what's happening. We actually had a local maximum at 0, and we had a local minimum at 4. We didn't know that until we graphed it. But the theorem, or this method says, look, who cares about the graph? If you're going to have an absolute max or min, if it's going to happen, it's going to happen either at the ends or at the critical numbers. So let's just plug those in to the function, compare them. The biggest one's your absolute max, smallest one's your absolute min, you're done. Questions? All right. I put up the video solutions to this homework set this morning. I did them. I did not do the first problems because they're visual, and I figured you could do those on your own. I'd say go for it, you know. There's nothing I haven't shown, there's no method that I haven't shown you. The thing I haven't shown you is more difficult functions. I mean, this is a polynomial, right? Setting the derivative equal to 0, that's pretty straightforward. But what happens when this function is more complicated? So that's what we're going to do next class. We'll do more examples of this. But you can at least start the homework and look at functions that are like polynomials. Just stick with those for now. And then if you want to try the others, you can. Thursday. I'm a little behind on grading. I know I owe y'all some grades.